Looks like it's working. There you go. All right. Looks like we're all set. Thanks so much for testing that stuff out. And we're ready to get started. So I'm going to go back to sharing the intro slides. That's not what I want. Oh, wrong app. This one. All right, I'm ready to go. Good morning or good afternoon or good evening, everyone. This is the Measurement Analysis for Protocols Research Group meeting online for IETF 110. Miria, my co-chair, and I are both on here. Miria is going to help with watching the Jabber channel and help keep me on track if I forget anything. You can reach us at maprgchairs@ietf.org if you ever need to. This session is being recorded, so it will be available like all the other Maprg presentations afterwards on the Maprg wiki. If you search Maprg wiki at Google, you'll find it, and there's an index to each individual presentation. Here's the IRTF notewell. It's the same as the IETF notewell, essentially, but be aware that speaking about your work here has potentially consequences having to do with intellectual property, and familiarize yourself with that. Here's the IRTF privacy and code of conduct. Behave yourselves, you always seem to. But look at that if you need to know anything about the details. Here's a slide about the goals of the IRTF. For those of you new to it, and I think maybe we have a couple speakers that haven't visited us before, the IRTF conducts research. It's not bound by the same rules as the IETF, but we largely focus on research that has to do with IETF things, and we happen to meet co-located or coincidentally with the IETF. Administrivia, you can find our charter online. I usually search for Maprg at Google and that comes up. There we have a mailing list if you want to stick with us in the future. Today's slides are not at meeting 105, they're at meeting 110. So I'll fix that in the slides. The Meetup link you've already got, and we're also on Jabber, so feel free to type things in the Jabber session, which should be on the left of your Meetup screen if you would rather do that than speak out loud. Our agenda for today is, once we get past this few minutes of intro, is we'll switch to Paul Hoffman for about 10 minutes talking about collecting typical domain names for web servers. And if you look at the agenda link on the website, the document or the report that Paul wrote, I think for ICANN is listed there, the link to it. Then we're going to bring Viet up to present work that was presented in an academic conference. The link there to the full paper is also there. For a 15-minute research presentation, again, about the DNS and TLS and some measurement results. We'll switch to Fong for assessing the privacy benefits of domain name encryption. That is also is going to be a published research paper. Maybe I've got them the other way around. One's upcoming and one has already been published. The link to the papers there. We'll spend a few minutes for a quick update from Robin Marks about QLog, and then we'll close out with Pete Heist in the last about 10 minutes. And if we get any time back along the way, we'll have more time for questions, but we're going to try to fit the questions and comments in between those or in the time itself. So that's the session for today. Any opening comments or questions or issues? All right.
Just want to quickly thank Spencer and Oliver for note-taking. I found 2 note-takers, so we're all set.
Awesome. Thank you so much. Okay, so we've got Paul up first. So Paul, if you get in the queue to share your screen, I can approve it. Oops, I hit, there we go. And I'm going to experiment with setting this timer.
Hang on a moment, it's open.
Yep. I'm hanging.
Chrome. Oh, well, let's see if this just worked or not. Share my screen. Sorry, it.
Nope. No
Should have
problem.
done this one first.
No problem. We're right on time.
Well, hell, I am not. I'm just going to do my entire screen, and so I'm not going to be able to see the timer or anything like that.
Okay. I'll
I can't find the
when
right. Oh wait, there's one that's yeah, application window. I guess we always have to start an IETF meeting with hardware issues.
Would you like me to stop you?
No, I'm just going to do my entire screen. I'm good.
But
If I'm
remember,
starting to run over, can you just interrupt me? Oh, it's not even letting me.
yeah,
You know what?
let
Why
me
don't we go to next presenter? And I believe I have to restart Chrome.
Okay. Didn't you just share your screen 5 minutes
No,
ago?
I did not.
Oh, okay.
No, we
Okay.
only did
Yeah,
the video.
yeah. That's the
Sorry
same
about
thing I had
that.
to do. I had to restart Chrome. Let's see.
Yeah, or
can
if we have the slides at hand, we can share for Paul, I
Oh,
guess.
if you can do that, that would be great. Your preference.
Yeah, let's just so that it stays with my notes. Then we'll do you first and keep Fiat where he was, and you just need to
Okay.
have patience with me for a minute to find the slides. Let's see. You are.
This was collecting typical domain names.
What was the last word in the name of the
Web
truncating
servers.
them. Servers, got it. Thank you. All right, so I'm going to share preview. I'm sorry. There we go. I've got
Beautiful. Thanks.
37 minutes after the hour, so I'll let you know when there's about 9 minutes up if you have not finished by then. Go ahead, Paul.
And I'm going to zip through this quickly. So greetings. My name is Paul Hoffman. I work for ICANN. This was work that I did under the auspices of ICANN, but it was actually initiated for the DPRIVE working group in the IETF. So next slide. So the motivation for this work was that in the DNS, a lot of people, when they're doing research on like authoritative servers and such like that, they want to collect data from a lot of authoritative servers. I'm going down and up again, but that happens. Typically what people do is they use one of the lists of the most popular, servers out there. So like the Alexa list or the Tranco list and such like that. But those aren't typical. And the request from DPRIVE was actually, we were trying to measure how long it takes to set up a TLS connection on a typical web server. Turns out we didn't end up using the research, but it was fun to do anyways. So the kinds of lists that people use, like I say, are the most popular websites. And if you don't know about Tranco, you should definitely look at the old Maprg slides on that. The other one that people use is they extract that all of the GTLDs, the global top-level domains, I'm sorry, generic top-level domains. Those are available, those lists of the domain names. However, a bazillion of those are just parked, so they're not really typical either. Or they get a dump from a passive DNS collection system, but that's not really typical because those are often very local. That is, for a recursive resolver in a particular region, it's going to be much more regional. Next slide. So what I all of a sudden just realized is that, wow, Wikipedia has links to a bazillion small websites. If you're reading the Wikipedia page, you will see things like personal websites of academics and lists of all of the elementary schools in a particular town in a country you've never visited and such like that. And also the nice thing is Wikipedia is not just in English, it's in pretty much every spoken language in the world. So these are examples of the kinds of things that as I was looking, I was like, oh, this is great. These are much more typical than a list of the largest websites around. You get governments of small cities, obscure sport teams, things like that. So the question was, well, great, without scraping all of Wikipedia, could I get a sample of these? Next slide. It turns out that they actually keep a database twice a month as backups, a public database. They want people backing up Wikipedia, basically to mirror it, not so that you're serving it, but in case they go down and such like that. And instead of them just having all of the pages as one giant hunk, they actually have pages and some subsets, and one of them is the list of all the external links. So that was perfect. I grabbed that for the research I did here. I did that at the beginning of this year. They update it, it seems like twice a month on the first of the month and then sometime towards the middle. So grab the database, extract all the external links because it's actually a database. It's a MySQL database. Clean up the lists because Wikipedia, it being publicly edited, you have lots of broken links that just in fact don't make sense, and that's okay. You know, like not dunking on Wikipedia at all. It's a lovely resource. Picked out all the ones that in this case were for HTTP and HTTPS, which turned out to be the vast majority of all of the links. Can you scroll down or keep it as a full screen?
I can.
Not that I wouldn't be.
No,
that's fine. Not that I
need
wouldn't
to
be
turn my
doing it
mic back on
myself.
so I can see you. No, thank you. I'll bring it back up to full screen.
No, that's
Just
fine. That's fine.
I'm just
Was
flying
that your
blind.
cat, by the way? So, so and then because what I was looking at is just web servers, I didn't care about the full URL. I stripped off the scheme and everything after the domain name, which means I didn't know which ones that had been listed as HTTP or HTTPS, but that's okay because one of the things we wanted to see is if you're hitting on a web server that actually doesn't have HTTPS, how long will it take for you to find out and such like that. So what this gave me was a list of all the domain names for all of the links. And then I had to cull the list because of course there was a lot of duplication. A million things point back to sites like Google, or for example, for a large university, there might be, you know, thousands of links. Next slide. So after I did all of that, and again, I did this for January 1st, there were about 750 databases. I got about 7.35 million unique domain names from the data set. So that was lovely and way more than I wanted. So I took a random sample of 100,000. But so the good news is if you want millions of unique domain names to sample from, this works just great. So, and I wanted to test 100,000 hosts, but many of the names in there are dead. So I actually started with over 100,000 and resolved them all. So I found out which ones actually currently have an IPv4 address. So I think I started with 150 and then 150,000 and ended up with about 110,000. And then I did the actual analysis that I was doing, which was timing, but I also wanted to look, just because everyone in the IETF says, well, how are we doing with IPv6? And how well, you know, for those of us in the DNS world, how many were DNSX signed? So I did that analysis as I was doing it. That's not important to this presentation. Basically, the presentation is about, hey, look, I found a new data set. You can find it too. Next slide.
Okay, Paul, you got about 2 minutes.
Yeah, and that's fine. So this is the last slide. So if this interests you, please take a look at this report. It's called the same as this one, Collecting Typical Domain Names from the Web. We have our own series in ICANN called the Octo series, which is the Office of the CTO, which is what I'm in. So there's an Octo number of that. And I don't actually give the code in there because, as someone pointed out, maybe Wikipedia doesn't want us pulling down the databases all the time and such like that. But if you're interested in doing this work, please get in touch with me. I do have a GitHub repo that I just haven't widely publicized for the steps I took, which is a bunch of, vaguely commented Python code, but it actually is reproducible. So that's it. I guess for those of you who care about the DNS and IPv6, about 17% of those domain names that had a v4 address also had a v6 address. And for those of you who care about DNSSEC, approximately 4% of those domain names were DNSSEC signed. So great. And I guess we're not doing questions, right? We're just moving on.
Yeah, we are. We have time. I see.
Okay,
I think we've got about 2 minutes. If anyone has
great.
got a comment or question.
Yep.
Excuse me for shutting the slide down, but I can't.
No, that's fine. That's fine. And the slides are available. So yeah.
Yeah. So for participants, put yourself in the queue if you're interested in speaking or submit to something to Jabber, and you can relay it. So we've got Alexander in the queue.
Thank you. Thanks, Paul. Alex Mayo from Nick.IT. I was wondering, did you also consider certificate transparency as a sort of domain name? Because I found that very interesting as well.
So that's a very interesting question. No, I didn't, but then last week I did. All of a sudden, someone had said, oh, but there's every certificate you want in CT. So I will probably rerun this at some point and see whether those numbers are any different. But no, I didn't at the time.
Cool. I like that. It's always good to know about another data source that's differently biased than all the other ones that we use. I wonder if also it'd be interesting to see after a time how many stale names are in the Wikipedia, and they might be able to use that for some of their update driving.
They actually don't do automatic updates, which I think is fine. I mean, they're really reliant on volunteers, and I think that's really good. And the other thing to note here is that this is not meant to be a typical of the web data set. It's more typical. For example, all of us probably in the last month have ordered out from a small local restaurant that had a website that is not in Wikipedia. There's probably millions of those. So,
okay, we got Oliver in the queue. Why don't you go quick, Oliver, and we'll close the queue then.
Yeah, sure. So this is Oliver. I have a question. So basically, initially you started with the assumption that the top lists out there are not really representative. Did you also basically compare the data set that you gathered from Wikipedia with the one what you got from?
Definitely.
Okay.
Yep. And so if you look at the report, you'll see that. So very briefly, IPv6 adoption was almost identical between Tranco and this. DNSSEC adoption was actually, so I remember I said it was 4% for this list. It's about 2% for the Tranco list. So that to me says that's a huge difference. That shows that in fact, well-managed popular websites are less likely to use DNSSEC than typical.
Cool, thanks.
Thanks a lot, guys. Thanks, Paul.
Thank you.
Let's bring Viet up. And Viet, you got a 15-minute slot in this short 1-hour meeting. So okay, I'm going to start the countdown clock, and I'll let you know when there's 2 minutes left or something.
Okay, so perfect. So hello, everyone. My name is Viet, and I have the honor to present our paper called Measuring DNS over TLS from the Edge here at today's Maprg meeting. So as Dave mentioned, this paper, which was co-authored by Irina and Viper, have also joined this session, as I could see, will also be presented at PAM later this month. And you can already find a link to the PDF and more details on the paper as covered in this talk on the GitHub repository linked here. So first of all, a brief overview of the main findings right away. So as the title of the paper suggests, we will be looking at the adoption, reliability, and response times of DNS over TLS, or DOT for short. So during the talk, we will see that the adoption of DOT is still rather low, and that we have higher failure rates and response times for DOT as one may expect compared to traditional DNS, but we will get back to these results at the end of the talk again. So we will move on, and as most of you likely also know, DOT was standardized in May 2016, so roughly 5 years ago. And its main feature is that it provides confidentiality by securing the DNS traffic with a TLS session between the DNS client and the resolver. Now, previous measurement studies have already looked at different aspects of DOT and have measured DOT from different networks and vantage points. However, not from home networks, which is what we were interested in. And so we were wondering, how does DOT look from home networks? In order to find this out, we kind of split our measurement study in two parts. And part one in this case is the adoption. And before looking into home networks in particular, we reproduced the first study that we just referenced, in which the authors have scanned the IPv4 address space for open DNS resolvers, and then subsequently checked the open IP endpoints that they found for DOT support. And as of April 2019, this was at 0.15% roughly. So we repeated this measurement approach and found that the number of open DOT resolvers has actually increased by roughly 23% over the course of 9 months. And that also the support for the new TLS 1.3 has also substantially increased among these open resolvers. Whereas on the flip side, the support for older versions like TLS 1 or TLS 1.1, the support for those has been also increasingly discontinued. So overall, we have found some decent progress regarding the support of DOT and newer TLS versions, although overall the adoption is still somewhat low. Then for the second part of the methodology, this concerns the reliability and response times. We use the RIPE Atlas platform for measurements, and this platform has been able to run DOT measurements since early 2018, roughly. So we reached out to RIPE NCC, and they kindly helped us with our measurement study, in which we involve around 3,000 residential probes, all of which are IPv4 capable, and version 3 RIPE Atlas probes in this case. So what these probes do is they issue DNS requests once a day over a period of 1 week. This was in July 2019. And they do these requests both over DOT and traditional DNS over UDP on port 53. And these DNS requests kind of request a record resolution for 200 domains over IPv4 towards a set of 15 different public resolvers, which you can see here in the table on the right-hand side. And on top of that, we also issue the DNS requests to the local resolvers of the RIPE Atlas probe. As you can also see in the table, 5 of the public resolvers support DOT already. And as for the local probes, this is not really, or we weren't really sure if those support DOT or not. So this ties back into the question of adoption of DOT. And for those, we found that only 13 probes of the more than 3,000 probes that we initially used had a point or received a DOT response successfully from their local resolvers, which is roughly 0.4% only. Nevertheless, overall, we collected around 90 million DNS measurements in total, which we will have a look at in the upcoming slides. So, okay, first of all, for reliability. We look at the reliability of DNS over TLS based on failure rates, which you can see in this table, which is also taken from the paper. The failure rate in this case is simply the column of number of failures divided by the total number of measurement column in this case. And obviously then the question would occur, what is a failure exactly? A failure in this case is when a probe is not able to send the DNS request to the resolver, or on the other hand, when the response was not received by the probe. So in both cases, the RIPE Atlas API returns an error along with an error message, which we had a look at and saw that the most common errors in this case for both traditional DNS and DNS over TLS were timeouts, errors related to sockets, to connect, and TCP and TLS related errors, which is obviously DOT exclusive since DNS over UDP doesn't use TCP or TLS either. So when comparing the failure rates for both protocols, in this case, especially for the resolvers that use both or that offer and support both protocols, you can see that DOT has higher failure rates. So there is some inflation regarding the failure rates, which range from just about 0.5 percentage point for Google and Cloudflare over to a few percentage points with Bot9 and clean browsing. And then lastly, with more than 30 percentage points for the local resolvers. Here, you can also see that uncensored DNS has an inflation of more than 95 percentage points, which indicates that there have been issues closer on the server side for DOT, whereas for the other DOT measurements, we see that the issues are closer to the probes and along the paths, indicating that the DOT traffic is simply dropped by some middle boxes, which also explains the high number of timeouts that we see for our measurements. Okay, moving on. We also take the previous table that we've seen and split this by region, by the location of the probe, to be more specific. And this is what it looks like. So this matrix shows the median failure rate for all the probes on a continent for a specific resolver in this case, with traditional DNS on top in the top matrix and DNS over TLS in the bottom one. So for DOT in particular, so the bottom part of the figure, we see that the failure rates are somewhat varying regarding the different continents and resolvers. So some cells have lower than 1% of a failure rate, whereas some other cells have close to or even more than 10%. And we also see that the majority of the cells which have higher failure rates are probes or belong to probes located in Africa and South America. So it seems like there are more issues with DOT in these or on these continents. As for the local resolvers, on the bottom figure, you can see that we only have results for probes in Europe and North America. As I mentioned before, we only saw local resolvers of 13 probes to return responses at all. And these kind of were both, all of these 13 probes were located in Europe and North America, respectively. With both of the failure rates being higher by quite a bit. So we have here failure rates of more than 30 to 40% compared to most of the other cells, which are mostly single-digit percentages for DOT. All right, moving on to the response times. So with RapAtlas, this is a bit more tricky, so some background explanation on that. For traditional DNS, obviously, you simply send out the request over UDP, and then the resolver will look up the requested domain either in its cache or recursively, and then send you back the response. Now for DOT, you obviously have the TCP and TLS handshakes before to establish the connection and session to secure the traffic. And typically a client would be reusing this session in order to get or minimize the overhead of these handshakes. Now for RapAtlas, this is a bit difficult and different since the measurements are designed to be independent from each other, which means that these connections and sessions are not kept alive in between the measurements, meaning that the response times that we measure here and present here always include the full handshake of the TCP and TLS handshakes. As a result, this will roughly resemble upper bounds for the DOT lookups, as subsequent domain lookups would not have to do the handshakes and be or have a lower response times. All right, so now also the part of the domain lookup may vary a bit. So in order to partially avoid this, we focus on the 5th percentiles of each probe and resolver tuple. And given that we repeat the measurements over a period of a week and take the response times towards the lower end of the distribution with the 5th percentiles, this will therefore approximate the cases of cached records. On this figure, on the right-hand side, you can see the CDF for these 5th percentiles. And for DOT, we can see that the medians are around 10 to 30 milliseconds for most of the resolvers, whereas for DOT, medians are roughly 130 to 150 milliseconds for the faster resolvers, going up to more than 200 milliseconds for some of the slower resolvers, and in this case, uncensored DNS is an outlier again at 1 second for median. So when comparing both of these, we can see that the response times for DOT are higher by more than 100 milliseconds when compared to traditional DNS, mostly due to the connection and session establishment. And before we saw that local resolvers have more failures than public ones for DOT, but in this case, the response times are actually somewhat comparable for these two types of resolvers. Now, lastly, again, we split this by regional aspects. I don't want to go into too much detail here, so just briefly going over it, this is how it looks. And we see that before the failure rates were somewhat varying, but now for the response times for DOT, DOT is highly varying regarding the cells on the bottom, which you can see. Although, again, we see higher values primarily for probes in Africa and South America. And also, as mentioned, for DOT, the failure rates were higher, but now for the local resolvers, we see somewhat comparable response times between local resolvers and public resolvers. So just to sum it up, in conclusion, we saw that the DOT adoption is still somewhat low, with less than 0.5% for both the IPv4 address space and the local resolvers of the RIPE Atlas probes, although there has been some decent progress regarding the increasing support of DOT and newer TLS versions. For the reliability, we saw that for DOT, failure rates are in some cases comparable, which was mostly the case for public resolvers when comparing to traditional DNS, and in some cases much higher, which was the case for the public resolvers. And we've also seen some indications that this is mostly due to issues along the path with middle boxes. And lastly, regarding the response times, we saw that DOT is slower by more than 100 milliseconds, largely due to the connection and session overhead, as I just mentioned, although the response times for public and local resolvers are somewhat comparable. And yeah, finally, as mentioned, all the measurement-related material is online on our GitHub repository, and also the paper with more details. And if you have any questions, you can feel free to send us an email, and I'm also happy to take questions right now if there are any.
Thanks, Viet. Yeah, we have a couple minutes for questions, so put yourself in the queue if you'd like to speak.
Yes, there was one comment about DOE compared to DOT in the chat. Are you planning to look at this as well?
Okay, so with RIPE Atlas, you cannot run DNS over HTTPS measurements. However, there are some papers that have already looked at that, so this is probably not something that we would be looking into, although there have been, as I said, some studies that already did that.
All right, thanks, Viet. In the interest of time, we're going to switch on. Thanks for bringing work that we scooped PAM on. You saw the results here before they're in PAM, which is one of the things that Miri and I try to do in this group, is bring you the measurement result before it's published. So thanks a lot.
Okay, thanks a lot.
So we have Fong up next, and just to prove that his share should work. There we go.
Okay, so can you
All
see
right,
my
go ahead.
screen now? Okay,
Yeah,
thank you.
And I'll start a timer, and I'll let you know if it's looking like you're having trouble with about 2 minutes in.
Okay, so hello everyone, my name is Fong. I'm a PhD candidate at Stony Brook University, and today I will be presenting our paper with the title Assessing the Privacy Benefits of Domain Name Encryption. And this is a joint work with researcher at Stony Brook University, UMass Amherst, and UIUC. And the work was actually presented last year in Asia CCS. So we all know that like the adoptions of TLS is increasing in recent years, and more network traffic get encrypted on the internet. And just to give you a sense of how much it's been increasing, this is the screenshot I just got yesterday from Let's Encrypt And they show that almost 250 million fully qualified domain has supported TLS connections. And regardless of the use of TLS and HTTPS, domain name is the last piece of information that has not been encrypted yet. And a domain name actually can be considered as important and sensitive as the content is hosted. So for example, this domain name, just based on the domain name, you can actually tell a user, say, online shopping activities, health conditions, religions, gender identities, or even sexual habits. So where is domain name actually exposed on the why? So this slide shows you like 2 common places where domain name information can be monitored by an on-pad attacker. And these are packets captured when visiting example.com. So the first place where domain name example.com exposed is through DNS queries and responses. And after getting back the IP address of example.com, the client initiates connection to port 443, start the 2S handshake, and this is the second place where domain name information is exposed. And this is because in previous TOS version until 1.2, the TOS handshake takes place before the actual encryption happens. So it exposes the domain name information on an extension called server name indication. So the exposure of domain name information in these 2 places allow any on-bad attacker to tamper with user connections. A malicious attacker can redirect a user to a destination where malware is hosted, or state sponsor sensor can interfere with user connections based on the domain name information seen on the DNS or SNI field. And so for the rest of these presentations, I will first introduce the basic concept of domain name encryptions protocols and the motivations behind our study, the methodologies that we use to conduct our measurement, and then I will show the analysis on the privacy benefit provided by domain name encryptions due to domain co-hosting and the dynamics of domain to IP mapping. And finally, I will discuss the potential approaches for domain owners and hosting providers to help with increasing the privacy benefit of domain name encryptions. So to address the previous security and privacy problems of plain text domain being exposed on the why, domain name encryption has been suggested in several proposals, with DOT come first. And here, DNS queries and responses will be transmitted over a TOS channel. And with DOH, DNS resolutions is performed over HTTPS. And of course, they're going to be through port 443 instead of 853. And therefore, inheriting all of the security and benefits of HTTPS protocol. And finally, starting with TOS version 1.3, the server name indications extensions in the client hello message during the TOS handshake can be encrypted. And with this proposal, the domain name information on both DNS and TOS handshake traffic can be secure. So in this new setting, a user and the DNS resolver first establish a channel. And this is an encrypted channel. It can be over HTTPS or over TOS. And after that, all of DNS queries and response are sent over this channel. And similarly, during the TOS handshake process, unlike in previous TOS version, in version 1.3, their server name indication will be encrypted too. I mean, this is an optional option. It's not compulsory. So in the RFC, it say that it's optional. So this new protocol will prevent any on-pad observer from seeing plain text domain name on the wire. So, however, in this new setting, the attacker can still see the IP address of the destination server. So actually, on this slide, that IP address is the actual IP address of example.com. So now the attacker will try to guess, okay, if this IP hosts only example.com or any other website. So here come the motivations of our study. Given that the destination IP addresses are still visible on pad to on-pad observer, we are interested in quantifying the potential improvement to user privacy that a full deployment of domain name encryption could achieve in practice. And the extent to which the inference can be easily made depend on 2 factors. First, whether all the domains are hosted on the same IP address or not. And second, the stability of mapping between a given domain and its hosting IP address over time. So here's the experiment setup. So we first create a set of test domain by aggregating domains from Alexa's and Majestic top lists from the last 30 days that give us a set of around 7.5 million domains per day. And next, we perform an active DNS measurements to resolve these domains into IP addresses. And finally, we analyze all of the domain to IP mappings and study their co-hosting degree and the dynamics of domain to IP mappings over a period of 2 months. And since many domains are hosted on CDNs, which is, they map the domain to IP to different IP at different locations. So we conduct our experiment across 9 different vantage points as shown on the map. So we try to distribute our vantage point in a way that their geographical distance are maximized from each order to capture the CDN behavior if there's any. And so we conduct our measurement for periods of 2 months to examine the dynamics of domain to IP mappings over time. So let's go back to the attack scenario in which the attacker can only see the IP address of the destination server. So given an IP address, there are 2 hosting possibilities. The first one we prefer to as single hosted, in which a domain is exclusively hosted on one or more IP addresses that do not host any other server, any other domain. So in this case, let's call K is the co-hosting degree. Then the co-hosting degree of example.com and all of its associated IP address is 1. And we refer to this hosting scenario as privacy detrimental. This is because from an adversary point of view, only seeing connections to this IP address alone is enough to infer which domain is being visited. And for the second possibility, we prefer to have multi-hosted, in which an IP address hosts more than one domain. And then in this case, example.com say is hosted on one or more IP addresses that also host many other domains. So the co-hosting degree for an IP address in this case is the number of domain hosted on it. And for the co-hosting degree of example.com, we compute it by taking the median of the co-hosting degree across all the IP addresses example.com is hosted on. And for this case, we prefer to a privacy beneficial case, because from the adversary point of view, they cannot easily say, okay, just by seeing the IP address, they cannot say which domain is actually being visited, because everything else were encrypted. So analyzing our data, we found 2.2 million unique IP addresses, of which 70% host only one domain names. So this means visitors of domain hosted on these addresses will not gain any privacy benefit by domain name encryption because of the one-to-one mapping between the domains and the IP address. And the rest, 30% of IP addresses host more than one domain. However, when considering the number of unique domains, so this plot is showing the number of unique IP address, but when we look at the number of unique domains, this 70% of IP addresses correspond to only 1.4 million domains, which is like 90% of our test data. And the rest 30% of IP address hosts 6.1 million domains, which is more than 80% of domains in our study, which shows some co-hosting degree among this group of 6.1 million domains. So next, we analyze the co-hosting degree as the percentage of all domains. So 90% of domains are single hosted, which means this domain will not gain any privacy benefit from domain name encryption. And the rest 80% of domains are co-hosted with more than one domain. And however, like there's around 40% here of co-hosted domain host with less than 10 domains. As we move toward the right-hand side, the co-hosting degree increase, and so there's the privacy benefit. So we assume that the co-hosting degree K need to be greater than 100 to provide some meaningful privacy, because an adversary in this case can only correctly guess a domain being visited with a probability less than 1%. So according to this plot, only about 30% of domain will gain some meaningful privacy benefit from domain name encryption because they co-hosted with more than 100 domains. So we investigate the top 10 hosting providers that offer the highest co-hosting degree per IP address. As shown in the third column right here, the average number of unit IP addresses observed for each provider is very low, with half of them hosting all domains on a single IP address. And we use the Hurricane Electric's BGP toolkit to confirm that these providers are actually very small providers, with many of them managing less than 10,000 IP addresses allocated by their regional internet authorities. And when looking at the popularities of domain hosted on this provider, as shown in the last column, the highest ranked one is at 386 positions hosted on Squarespace, while more than half of these providers host domain are well below top 10,000. So the takeaway here is that small providers tend to co-host a large number of less popular domains on a small number of IP addresses. And then we investigate the top co-hosting degree, by major providers that dominate the largest number of unit IP addresses. So this two table lists the top 20 major hosting CDN providers with more than 5,000 unit IP address that we observe. So unlike small hosting provider, the major provider hosts more popular domain. And as you can see in the last column, most popular domain hosted by this provider are well within the top 10,000 rank. However, in contrast to the small providers, the co-hosting degree per IP address offered by this provider is quite low, except for Cloudflare in this case, with the co-hosting degree of 16 domains per IP address that we see from our experiment. The rest of the providers host, let's say, less than 10 domain per IP address. So this observations show that major providers host more popular domain, but having a much lower co-hosting degree. So the previous two plot.
You got
sorry
2 minutes. I just want to let you know you have about 2 minutes.
2 minutes. Okay. So the previous two slides show the two ends of a privacy spectrum. That on the right hand side, there's domain that co-hosted, less popular domain that co-hosted on together with benefit from the domain name encryptions. But on the right hand side, there's more popular domain, but they're not co-hosted with any other domains, and thus receive less privacy benefit from domain name encryption. So let me skip this slide. Okay, so let's go to the dynamic of domain to IP mapping. So we conduct our measurements over 2-month period, and we see that there's 22.7 million domain to IP mappings, and the dynamics 80% of them are very dynamic, which means they survive for only 4 days, and only 13% of them are stable. However, if we look at the number of unit domains, there's only 0.2 million domains that are dynamic, and the rest, 92% of the domain, are very stable. So the takeaway is most domains are hosted on static IP address, which doesn't change over time. So in summary, regardless of the trend of co-locations on the web, domain name encryption cannot really provide meaningful privacy benefit with the current degree of domain to domain co-hosting, since the IP address information can still visible to any on-path observer. And to that end, we make these two recommendations. Three. First, the full domain name confidentiality must be preserved on both DNS and TLS channel. Otherwise, neither technology can provide actual privacy benefit. Just like Viet says in the previous presentation, that the adoption of DOT is very low. And we can see more of that in DOH, but still, like the ESNI adoption out there is still really small, like only Cloudflare right now supporting it. And for domain owner, they can seek providers that offer a high co-hosting degree per IP address, or like high dynamic domain to IP mapping. And finally, hosting provider can help increase the co-hosting degree by grouping more websites under the same IP, or frequently rotate domain to IP mappings to further improve privacy benefit offered by domain name encryption. And thanks for your attention. And we make our dataset available in this URL on the slide. You can get it. It's publicly available. And if you have any questions, feel free to send it to my email. Thank you.
Thanks a lot, Phong. Okay, so you can reach Phong at that address. We got a couple people in the queue. Let's take them. That'll be Andrew and Eric. Let's make it quick because we only have an hour meeting here. Okay. And then we'll switch to Robin. So Andrew, go ahead.
Yeah, hi. Thanks, by the way. It was a very interesting presentation and good, robust data. I just wanted to highlight, a couple of us made a point in the chat that I think you made a good case for the privacy benefits of co-location and so on, or using CDNs. Did you consider, though, the potential privacy risks and also security risks of increased centralization? Because potentially you're, if you like, encouraging centralization to get privacy, but you also sacrifice privacy with centralization. So I don't know if you've given that any thought at all. Thank you.
Yeah, actually, this is another paper that actually we wrote last year, submitted to NDS Maprg about centralizing all of the DNS query just to a single resolver. Like a lot of privacy controversial happening there, especially with Cloudflare and Firefox. To me, that is terrible too. Like we don't want to give all of our browsing history just to one single resolver, say Cloudflare. So to me, like this is orthogonal to what I just present here, but in terms of DNS queries, in another paper, we suggest that we should split them out, distribute it across number resolver, so that your browsing history is not known by just a single actor. So yes, centralization is terrible.
Thanks.
Well, that's my cue, I think. Eric Corlum is on. So we actually did look at what you suggest in terms of spamming the queries across multiple resolvers. The problem is that every resolver gets a partial copy of your browsing history, and given how much redundancy in the browsing history actually makes the problem worse, not better. So if you have a fix for that, I'd be interested in hearing it. But the reason I got up actually was to ask, and Martin Thompson and Yuri Yarko had a document on this actually, and Ted Hardy, I believe. So the reason I got up actually was to ask. Have you done any assessment on the sort of relative impact of the actual size of the anonymity set? So I mean, like in some cases, 10 is quite good, right? If it's like Facebook and Telegram, that actually concealing Telegram's traffic in Facebook is quite valuable. On the other hand, and also there's I think a question about how much does reducing the anonymity set help with traffic analysis attacks? Because I know there's been a lot of work on that, and those typically don't work well if you have a very large number of domains, but they work quite well when you have a small number of domains.
Cool. Yeah. So thank you for the questions. So in terms of sensitivity of a website, it's really debatable here. Like what should be considered sensitive, what is not. And like if you go to just an IP within the range of say the AS Google, whatever you use, YouTube, Google Map, or whatever, Gmail, people don't really care. But in terms of sensitive, the anonymity set here, sometimes a set can be 100, and if just one of them in there is sensitive, then that whole set can be really sensitive. Actually, we have a follow-up work on this, and we actually do traffic analysis on a single website per website. And for 200, we analyze 200,000 websites, include half of them are popular and half of them are sensitive websites. And just based on the IP address, you can pinpoint more than 90% precisely what even like the sensitive website in the long tail with the k-anonymity really high, but you can still pinpoint it with really high precision based just on the IP address.
Okay, thanks, guys. I'm sorry I have to cut you off. We're doing this experiment with these hour-long meetings. If you write to the chairs between the meetings if you think we should do something different. And I'm sorry I dropped Eric from the queue just because we're going to run a couple minutes over so that we can keep the session lengths for the other two presenters. Thanks a lot, Fong. Robin, can you open your slides, or do you need me to do it? We're seeing your whole screen.
Should be fine.
Yep, thanks. Looks good. Go ahead. I'll start a timer and I'll let you know when you have a minute left.
Yep. All right, so let's talk QLog again. So QLog stands for quick logging, which is an effort started about 2 years ago to make the new Quick and H3 protocols a bit easier to debug and analyze. Because typically what you would do is you would take a network packet capture at some point and then use something like Wireshark to analyze that. And that's of course still possible with Quick, but more difficult because Quick encrypts almost its entire transport layer as well. So to do this, you would have to store the entire packet capture, including the full payload, leading to some scalability and privacy issues. I'm sure some of you have experienced this with encrypted application layer protocols in the past as well. There's a second long-standing problem with this, and that is that not all aspects of the protocol are reflected on the wire. For example, for transport, things like congestion control typically aren't seen, and so difficult to analyze. So the solution that we proposed for Quick was to instead move to logging at the endpoints directly in the implementations themselves. The core thing there is that we propose to do this in a standardized way. So there's a single format, a single schema that all of the implementations follow, making it easier to create reusable tooling and also to share data in between. And that's of course not rocket science. It's relatively simple. As you can see here, for now we are using JSON as a serialization format. And we just define, if you want to log a received packet, these are the fields that you should log. If you want to do something with congestion control on the right side, these are the fields that you should log in. This is what they should look like, and so on. Using this across implementations is powerful because then we can build some tools, which we have done in what is called the QViz project, giving us, for example, this kind of sequence diagram showing packets going back and forth, and also the metadata on the implementations, but also quite powerful congestion control debugging tools. Quite interesting because in Quick it's much easier to experiment with different congestion controllers over time. This approach of having a shared format and reusable tools has turned out quite interesting and powerful, leading to the majority of the Quick implementations actually outputting this format. Most notably, Facebook is using this in production to help analyze their deployment of Quick and HTTP3 at scale. Because of this relative success, we now have plans to adopt QLog in the Quick working group. They have been separate drafts until now, but so we're moving to adoption soon. And our goal there is not just to flesh this out for Quick and H3, but also to start looking at how we can bring this to different protocols and different use cases as well. Because as you can imagine, this type of approach can be very useful, not just for Quick and H3, but also, for example, the things that we've listed below here. One particular one I wanted to highlight is the bottom one, where we have a project that we are trying to log both very high-level adaptive bitrate video streaming algorithm metadata, together with the relatively low-level Quick congestion control parameters, to try and assess how we can better match them up against each other. I think from a research perspective, and that's why I want to bring this to the Maprg, I think this approach will make it much easier to compare different implementations of protocols, which in my opinion is something that is often severely lacking in the academic research community to date. I also think it would be much easier, make it much easier to share data sets and to reuse them or revalidate results. And then my hope is also that we might, in this way, get a bit more access to actual production or deployment level data sets, if they can be properly anonymized first, of course. For example, Facebook has concretely indicated interest in exposing a larger data set, with, of course, all the salient data removed again, to make it easier to do actual research on real-life network data, which I think is a bit lacking as well, or at least difficult to get access to for the broader community. One example of that is Christian Rietema, who has already done something similar using public Q-logs from the quick interoperability servers. So they have their public servers, they expose their Q-logs for debugging purposes. And he already tried to measure, for example, what are realistic packet loss patterns and what are causing them using these public Q-logs.
Cool. Thanks, Robin. Can you wrap it up?
Yeah, this is the last slide.
Cool.
So I would say if you're in any way interested in this type of thing, join us in the quick working group or let us know on GitHub. Thank you.
Okay, quick question or comment. Thanks, Robin, for bringing that update and accommodating our tight schedule and pointing people to that tool. All right, so let's get, so we're going to run about 10 minutes over here. And we got, let's Pete. Yeah, we got Pete ready to go. We're about 10 minutes over. You guys got a half an hour until the next IETF meeting if you want to catch one. So apologies for running late. Pete, I'm going to approve your screen share.
All right, you got the slides?
Yep, it's up, and I'll set the timer for 10 minutes, and you're ready to go.
Thank you. All right. Welcome to the ECN Deployment Observations Talk. I'm Pete Heist, and I'll try to move through these slides briskly in case there's a question or two at the end. We've got Jonathan Morton here as well for that part if needed. So why did we go to the trouble of gathering data on ECN at an ISP's border router? Well, there are a few questions we'd like to answer for ECN engineering. For endpoints, we'd like to know what proportion of flows are ECN capable and how many clients are initiating ECN. For middle boxes, we'd like to know what proportion of paths appear to have 3168 marking AQMs, so we know to what extent future experiments need to take that into account. We'd also like to know about any unexpected uses of the ECN field, since the signaling methods and failure modes are crucial for effective congestion control. My cautionary note here is we think of this study as informative rather than authoritative, given its size and fixed location. However, some of the results should still be useful and suggestive. So some basic facts about the ISP where data was collected. These numbers give some sense of scale. In any case, I'm grateful to Freenet Libidets for running my scripts and collecting the data for me on their production gateway. So how do we actually collect this data? We use Linux, IP tables, and IP sets. IP sets are essentially in-kernel hash tables using a specified key of interest, like IP address or IP and port, and mapping to a packet and byte count. The nice thing about them is that the quantity of data produced is relatively small and easy to process, and also you have fewer privacy concerns than with packet captures, as we're just counting packets meeting certain criteria. On the other hand, we don't have the benefit of deeper packet inspection or flow level analysis, so there are some questions we can't answer, like exactly what applications are setting the bits. For performance, we avoided anything that could cause a hash table lookup per packet, as some lab test cautioned us against doing that in production. So that leaves us without much detail on not ECT packets, which we can mostly live without. So here's what we observed from the endpoints. There are two main things to take away from this. One is that ECN initiation seemed relatively low, but also fairly widespread. And the second is that server acceptance appeared high. Starting with the servers, that should be easy to explain, as most server OSs have supported ECN acceptance for some time now. As for the clients, since we consider an ECN SYNAC coming back to an IP as indication that the IP has initiated ECN, that 44% number may be a bit too high as a proxy for the percentage of IPs truly using ECN, as port scanning or other unforeseen sources of ECN SYNACs drive that number up. For a rough sense of the distribution, though, around 35% of IPs received at least 1,000 ECN SYNACs, which is still a pretty high percentage relative to the percentage of flows that are likely to be ECN capable. Now on to how we detect AQM activity. At a gateway or middle box, ECE is sometimes a more reliable indicator of congestion than CE, because if we have an AQM downstream from the gateway, we won't see any CE marks since they happen after packets have already passed through the gateway. But we'll see the reflected ECE marks in any case, providing the transport headers aren't encrypted. So we mainly look for non-zero ECT0 in both directions and non-zero EC in either direction. However, we did see some anomalies in the signaling data that appear to come from the OS fingerprinting routines of port scanners. To help explain how we attempt to filter these out, with the IP in the middle here, ending in 140.73, we have CE and ECE marks with a ratio close to 1:1, which doesn't look like AQM activity. What we do is, if the ECE to CE ratio is greater than 2:1, we consider it possible AQM activity. If it's less than 2:1, we subtract the EC marks from the ones in the opposite direction, and if there are any left over, we consider it possible AQM activity, otherwise we don't. The detection isn't perfect, so there may be false positives and negatives, but we can also say that we likely miss some AQMs because we need both ECN flows and congestion to find them. And as we'll see on the next slide, that doesn't appear to be that easy. So now we want to take a look at, given that ECN was negotiated, how often was any AQM activity actually detected? First, I should point out, we have some known AQMs deployed, namely FQCODL is being used for 2 subnets. Since I helped write the script to deploy these AQMs, you might say, Pete, you've affected the outcome of the results, and that is true. But it turns out that the knowledge of AQM deployment also gives a better look at what the stats look like when there is a known AQM and helps us pin down how well we're detecting AQMs. But we do not include these known AQM subnets among the so-called random paths since we influence them. So what we did here is split the IPs into those that pass through a known AQM and those that do not. In the table, we see that 60% of ECN negotiating user IPs with a known AQM saw possible AQM activity, which roughly represents our detection rate. Well, after observations for 3 weeks, why isn't our detection rate 100%? That's very likely because, as noted before, you need both an ECN-capable flow and congestion to see it. So we simply might miss it, especially if there are AQMs in devices that don't often see congestion. Next, that 10.3% value in amber, that's our rough proxy for the percentage of random paths that may have an AQM deployed. Assuming that we've missed them at the same rate as the known paths, we could arguably scale that up from 10% to about 1 in 6, but to be more conservative, we haven't done that here. Finally, given that we've probably not classified all the AQM activity correctly and that we've missed some AQMs, 10% plus or minus an order of magnitude is about what we can reliably say. As for ECN endpoints set for non-TCP protocols, I'll go through this relatively quickly, but unlike TCP, the data for non-TCP is less clearly attributable to ECN because we apparently observed at least some misuse of the field. For one, the proportion of marks from the WAN is higher than one would expect, even taking into account the 10:1 ratio of traffic between the WAN and LAN. And I'll also note that we saw one IP with clear misuse of the currently unallocated ECT1, which accounted for some 97% of the ECT1 usage in total. That could potentially have been a large peer-to-peer download from a misconfigured peer, but in any case, this confirms that at least occasional and sometimes spectacular misuse of the ECN field does happen. So what are the possible reasons for ECN use on non-TCP protocols at all? There could be tunneled ECN traffic, but since there are different methods of encapsulation of the ECN field, and since those can be asymmetric, it's hard to say. Based on the ports we saw in use, like IPsec NAT traversal and WireGuard, we almost certainly saw tunneled traffic, but tunneled ECN traffic, we can't say definitively. And this study didn't look at protocols not supported by Contract, which, for example, includes IPsec ESP packets using IP protocol number 50. There was some discussion on the list that we could be seeing quick ECN here. That's also a possibility in at least one IP desport pair we saw, but again, we can't say for sure without deeper packet inspection. We think there's very likely to be misuse of the ECN field going on here, and we speculate by BitTorrent traffic. The now obsolete RFC 1349 defines a value for minimized monetary cost that conflicts with ECT0. And if a developer also forgets to shift that obsolete value to the left by 1, they might end up with an ECT1 as well. We did not see extensive marking on non-TCP traffic overall, but what we did see is that misuse of the ECN field can be expected from time to time. So thanks for listening, and if anyone wants to repeat this experiment somewhere else, I'll try to help support that. It should be possible to scale the collection script up to larger networks, but it should first undergo another revision to address some of the limitations mentioned in the draft. So with that, I don't know if we have any time left for questions, so I'll leave that up to the chairs.
Thanks a lot, Pete. We don't have anyone in queue. I think I'd like to cut it just because we're running 10 minutes over. I really appreciate you guys fitting into our just hour-long meeting. And Maria, any closing thought?
No.
Okay,
I think
we're ready to go.
Go ahead.
Thanks for joining us. Thanks for joining, everyone. We had about 135 people Really nice. I would love to know if what you think about the meeting length. We did these 2 one-hour meeting experiments to try to throw as much as quickly as we can as possible to you, but we can certainly do something else next time. Take care.
Have a good week. Bye.